This ESS IB Environmental Systems revision video, and today we're looking at topic 6.4 acid deposition, and we'll be focusing on how it is formed and the impact of acid deposition. So effectively you need to understand what acid deposition is. So acid deposition is the term for any acid coming down to the terrestrial system from the air, and there are two forms: wet deposition, which would be snow and rain. I suppose also it could be hail as well, and dry deposition, which would be ash or dry particulates. Now, normal rainwater has a pH of up to the level of, rainwater is acidic, classed as acid rain when it's below pH 5.6. So that's when it's acidic. Rainwater is naturally acidic. So if it was 6.6, it would be classed as normal rainwater. Now, this all links to obviously pH and acid, and the pH scale is 1 to 14. 7 is neutral, so pure water would be 7. Anything less is acidic, anything more is alkaline. And acids, the thing that makes an acid is it releases hydrogens into liquid, which can affect stuff like enzymes. And effectively, the pH is a logarithmic scale. So as I go from pH 7 down to pH 6, down to pH 5, down to pH 4, down to 2, 3, to 2, to 1. To 1. Each time I do that, the pH scale is, the number of hydrogens is increasing 10 times. So the number of hydrogens is going up by 10 because it is logarithmic. So pH 5 is 10 times more hydrogens than pH 6. How does acid deposition happen? Well, I'm going to focus on acid rain because I think then I don't have to keep changing the words, but effectively this could be the same for snow that's got acid in it as well. So effectively what we have is in gases, and normally we talk about, not in gases, in fossil fuels, and the two fossil fuels we're really talking about here is coal mainly, but also oil. There is nitrogen and sulfur impurities. So what an impurity means is we don't want them in the fuel. It is just in there and it doesn't help us at all. So what happens is when we burn fuels in the power station, nitrogen reacts with oxygen, for example, or sulfur reacts with oxygen to make nitrogen dioxide or sulfur dioxide. So nitrogen dioxide in this case is being emitted from the factories, and that goes into the air. Nitrogen dioxide is soluble, so what that means is it goes into the clouds. It will then dissolve into the water in clouds, and as a result nitrogen dioxide will become nitric acid, and sulfur dioxide will become sulfuric acid, and then that acid rain will fall as normal when rain would fall. That then goes into the trees, into the rivers, and into buildings, and can cause problems. So what are these problems? What are the direct effects of acid rain? So the direct effects are it will weaken the tree growth by damaging the roots of the tree when it goes into the soil, but also the leaves of the tree. And if the leaves are damaged, the plants can do less photosynthesis. It will harm aquatic organisms by lowering the pH, and that change in pH then causes the aquatic organisms to suffer, and it doesn't help with oxygen uptake. Indirect effects, though, so the ones that are not directly noticeable, it has toxic effects because it will increase the solubility of metal ions. So what that means is metal ions, which are normally in the soil, for example, will become more soluble. They'll go into the water. That will be toxic to fish, and if it's soluble, it means the plants can absorb it, and therefore that'll be toxic to the plants. These toxins then leachate, which means they go into the water, and as a result that can cause significant problems. So here we can see sort of a flow diagram of this. The acid rain goes into the soil. It can go directly affecting the soil pH. That can affect plants, so ones that are acid tolerant will increase in numbers, acid non-tolerant or non-resistant will go down, and that will lower then the biodiversity. The indirect effect of that is that it will cause the mobility of water, it will change oxygen availability and nutrient availability and increase its chance of heavy metals going into the plant, and again that will lower the biodiversity. So we need to focus a bit more on coniferous forests. Okay, so conifers are a particular type of tree that is likely to be affected by acid rain. And basically, if the conifers have acid rain, their leaves will lose chlorophyll. Okay, that's the green bit of the leaves, which will make the leaves in turn turn yellow. This means that photosynthesis rates will decrease and their growth will become limited. Leaf damage also allows the plants to get affected by pathogens, so disease-causing microbes and insects. And what will also happen is the soil loses nutrients into local waterways because it becomes more soluble as a result of the acid. Some plants have something called a symbiotic relationship. Think about the nitrogen cycle. There's something called rhizobium, and what the rhizobium do is help plants absorb nitrogen from the soil. These rhizobium bacteria will die if the soil has acid in it, and therefore less minerals can be uptaken by the plant. Also, aluminium ions, which are normally held in other compounds, get released by the acid, and that can cause root hair cell damage, so less uptake again can happen by that plant. So this aluminium ion release, let's have a little bit more of a look at this. Aluminium is common in soils. It's one of the most common elements in the ground. But when it's in the soil, it is not soluble. However, if the pH lowers due to acid, it becomes more soluble and it will leach out of the soil into local areas as a result. Now, this increases two problems. This causes a loss of soil fertility because nutrients in the soil might get washed away in the acid. So whilst we're talking about aluminium there, three important nutrients that get washed away with the acid is calcium, magnesium and potassium. And also the nitrogen fixing bacteria, as we said a few minutes ago, gets killed by the acid, and therefore less nitrogen can be uptaken because the rhizobium are dead as a result. Now, when aluminium goes into water, even at low concentrations, it will have an effect because it affects fish, stopping their ability to regulate salt and water levels in the body. It also stops normal intake of oxygen, so the fish will slowly die because of a loss of salt in the body and a lack of oxygen. In high concentrations, solid bits of aluminium will form on the gills, so less gas can get in, less oxygen can get in, and therefore the fish will die because they can't do enough aerobic respiration. So how can we measure the impacts of acid? What are the impacts generally of acid deposition? Well, other than the impacts we just talked about on plants and fish, lichens are also an important thing. So you'll be aware that lichens are biological indicators, which means that they are affected by sulfur dioxide and nitrogen dioxide in the air. And particularly sensitive to sulfur dioxide levels. And most of these will not survive, therefore, in high levels of acidity. And you can see here where lichens tend to live in the UK, very few near Birmingham, very few near London, and sort of Manchester area, Cardiff sort of area here, because of the amount of pollution. Peat bogs are something that's quite important in the battle against climate change. So peat bogs are partially decayed organic matter in the soil, and they're an important carbon sink. So basically they are leaves that haven't completely rotted away, and therefore they trap a lot of carbon in them. Acid rain will actually reduce the methane emissions of carbon sinks by 40%, and that is because they will the bacteria that decomposes in the peat bogs will will actually be killed, and therefore the acid rain could actually be useful in stopping carbon dioxide and methane emissions. Impacts of acid rain directly on human health. If breathed in, they can cause lung conditions such as asthma and bronchitis. And buildings made out of limestone, you can see here, reacts. So here's a statue before and after acid rain, and you can see the impact. There are regional impacts, however, which makes acid rain difficult to deal with. It seldomly travels more than a few thousand kilometres, so it normally is deposited in regional areas, often downwind. So, for example, in the past, the UK produced a lot of acid rain, and that acid rain travelled towards Norway and Scandinavia, and that caused them to get the issues, even though they were a greener country than us. The two different types, because obviously we're talking about acid deposition in total. Dry deposition happens to be a lot closer to the source and consists of these three gases, whereas acid rain can travel further distances, and that will obviously fall as nitric acid. Now, as I said, it doesn't travel very far. It normally goes downhill. So you can see here the map, which I mentioned before. A lot of the pollution can travel according to the wind. So you can see here there is particularly high levels of acid rain in this sort of area in Europe, and depending on where the wind goes, depends on where the acid rain sort of comes. And also the UK creates some which makes it go that way as well. Now, soil geology is important because some soils are more resistant to acid rain. If your soil is made of limestone, limestone is an alkaline, and therefore it is likely that it will have less impact, because if you take an acid and add it to an alkali, then you get water and salt. So if you're adding it to an alkali soil, your acid rain is going to have less an effect. But soils that are already acidic will have obviously a rapid decline in pH. And here's some graphs. You can see how the amount of acid rain has changed in Europe as over 20 years, as our knowledge of it has massively increased. So the second section of this video is, well, how do we actually monitor pollution and manage pollution to do with acid deposition? This was first looked at using something called the Gothenburg Protocol in 1990. And basically this protocol encouraged the idea that we need to reduce sulfur dioxide and nitrogen oxide emissions. And you can see on this graph how the sulfur dioxide emissions increased and then have started to decrease globally, they sort of, on this one, the nitrogen oxide levels have increased and then they've started to level off as a result. But you can see here how globally different countries are contributing, and this is where the blame game sort of comes in some respects, because it was countries that were industrialized first, which sort of North America, Europe, which had the higher levels in sort of 1950s to 1980s. However, their levels have massively decreased, and now it's the fastly developing countries such as China who have got the highest levels now. And some people say, well, you were allowed to do it in the past, we should be allowed to do it now. So what we need to think of is, well, how can we reduce this acid rain deposition or acid deposition? So we need to think about what the causes are, what the transfer is, and what the effects are. So if we look at the cause of acid rain and how we could stop this, the main causes are cars, buses and taxis. So we need to reduce the need for private cars, promote cycle and bus lanes, restrict areas like urban areas where the pollution will build up for cars, and promote cleaner fuels such as electrical models of cars. Electricity needs to be benefited and used in terms of to power cars, and therefore we need alternative energy production, i.e. green energy production such as wind, that doesn't release any of these pollutants into the atmosphere. We need to look then at using alternative fuels and alternative sources, and therefore the effects will hopefully be limited. But in terms of effects, we also need to look at how we can limit the effects on soil. This would be using lime. So I talked about limestone earlier, which reduces the acidity of soil, which means it will neutralize acid rain. In water, we use to monitor the plankton indicator species and the freshwater invertebrates to gauge the recovery of areas. and in living organisms we need to maybe capture and do captive breeding in protected areas for organisms that might be endangered until we can prevent the release of acid rain. So if we have a look at the EU's response and how successful it was using this protocol, we had a 50% reduction in acid rain or acid deposition by between 1990 and 2000. And developing countries now, however, are the ones that are increasing the emissions compared to the more developed countries before. And basically, though, the regional EU directive is any power station should not release a certain amount of acid rain if they're over 550 megawatts of energy being produced. And you can see here the timelines. It's a long timeline of how they've tried to reduce acid rain since it was initially come up with, and stages, and it's been renewed and renewed to try and. So if we look at around the world, it's not just Europe that's massively cut down on their acid production. The US has also attempted this. So you can look at this and think, well, was the US successful? So here you can see the amount of acid or sulfur dioxide emitted in the US was significantly high in the more industrial areas on the East Coast, and that was in 1989 to 1991. By the year 2007, that had massively decreased, so the American response was a success in that respect. You can also see here in the US emissions how things decreased. So you can see that nitrogen oxide has significantly decreased, sulfur dioxide has decreased by more, and that is really important as it is used particularly in industries that they have managed to do this and achieve these levels. Obviously they can still go down more, but that is a massive reduction. And again, this is happening in America because they've modelled acid rain, they've identified the problem, and they've done different experiments and agreed different rules on what can and can't be done. So again, how can we reduce the impacts of acid rain? We can lime lakes, and in Sweden they've experimented adding powdered limestone, as you can see here, to the lakes, but anytime new water is added, that will be diluted. So you can see here when you add limestone in, first of all, the percentages of low pH, which has got a really low pH, is high, but over time it will be diluted by new water added to the stream. Now, some would criticise liming lakes because it only covers the problem, it doesn't stop the cause. So if you keep adding acid, you're going to keep having to add limestone as well. The biodiversity isn't restored from the life originally lost, and limestone has a natural impact on natural nutrient balance in the lake and therefore could affect biodiversity as well. In terms of decreasing the effects of it, we can obviously reduce emissions. So we can use less electricity, so less power station emissions can be used. And we can do this through greener energy generation, such as wind and hydroelectricity rather than coal and oil power stations. We can use more nuclear fuel, which means there's no emissions of sulfur dioxide or NO2, so really important that you realise that it gives absolutely no sulfur dioxide or nitrogen oxide. We can use more efficient devices, so less is needed, and we can use biofuel, although which doesn't have these impurities, but obviously biofuel can be often used like oilseed rape, but that means food prices go up and that can cause hunger issues. And you can see here the sort of change in energy usage going across Europe, and now that wind power is increasing, hydroelectric is increasing, and therefore these things are positive. And you can see here electricity generation that is renewable across Europe. Austria now have 79%, okay, and you can see a high number, and obviously if one country is doing this, the other countries will tend to move that way as well. Now, how can we reduce the effects? We can also do pre-combustion techniques, so we can remove the sulfur from the fuel. So petrol, for example, in the UK is sulfur-free. That has cost extra money because the sulfur can be taken out using chemical engineering. That sulfur then can be obtained and used in industry, so it has a second benefit. We can also do what we call end of pipe measures. So basically at the end of a power station where the gases are released, we can have something called a waste scrubber. Now a waste scrubber, you don't need to know how it works, but effectively it catches the sulfur dioxide and nitrogen oxide. And also an example of this in more individual level, which most people's cars now have, is something called a catalytic converter, which prevents the release of nitrogen oxide. So there you go, that would be an example there of a waste scrubber here in the end of the power station. Okay, and a catalytic converter is part of a car which uses platinum as a catalyst to react with the nitrogen and prevent it being released.